Perfect. If everybody doesn't mind, let's still open with a prayer. Dear Lord, we thank you again for bringing us together. We're sorry we missed last week, but we thank you so much for the snow and the precipitation. We thank you for this evening. I thank you that more than one person came back. We'd pray that you please bless our time together and pray that everyone have a safe trip home. In Jesus' name we pray, amen. All right. Well, again, I appreciate everybody coming out tonight. This session's a little different, a little more focused than the last one. As you recall, last time we talked about why we're talking about this. This is the first of many sessions getting into some of the details of the various problems with evolution in general. I did get a couple of important feedback. One is that a green pointer shows up better than a red pointer, so I really appreciate Dave bringing me a green pointer. I may invest in one myself. The second one was I got a couple of, hey, great talk. It was over my head. Yeah, I know. So and there will be, like we talked about, there will be parts that'll probably be a little bit technical. I am happy to entertain any questions anytime, either during or after the talk. I am also happy to answer email. I appreciate those of you who emailed me, and if you have specific questions, please feel free to reach out. I'm pretty OCD about my email, so I try to get back in a reasonable time. So, on the note of things being a little complex, I added a couple slides in review just to make sure we're kind of trying to get everybody back on the same page. But in just broad spectrum, talking about what we talked about last week, why are we here? Why is this important to discuss? Well, like we talked about last week, if you destroy the foundation of something, you destroy the whole thing. And the foundation of the Bible is Genesis, and it's Genesis 1 through 11. It explains why are we here. Secularists have worked very, very hard to convince us that Genesis 1 through 11 is allegory or myth or whatever other term they want to use to destroy it, which ultimately leads more and more people to question their faith in general, which unfortunately leads them to ultimately question the existence and resurrection of Jesus Christ. And that's why we're here, is that I want everybody to understand the Bible is the inerrant Word of God. Quote-unquote science is subservient to it, not vice versa. We don't say, well, science says, therefore the Bible is wrong. We say, the Bible says, therefore your so-called science is wrong. On evolution, we talked about that evolution simply means change over time. And I think it's important that we distinguish between microevolution, which is change within a species, say you've got a pit bull versus a Yorkie, versus macroevolution, which is a Yorkie turning into a human, that you've changed between or into other species. Now, the theory of evolution is that through natural selection, which you've all heard, or quote-unquote survival of the fittest, we all started from single-celled organism and worked our way up through the complexity of the zoo to get to modern humans. And the idea being that a gene mutation creates a survival advantage that allows an organism to somehow become dominant and then pass on those genes better than the so-called lesser version of that variant. Again, a classic example being the neck of the giraffe. You start with a very short-necked giraffe. He slowly can eat something a little higher and a little higher and a little higher, and the poor short-necked guy dies out while the high guy lives a mighty life feasting. So a brief review on the genetics, where I know I lost a few of you, so I'm gonna try one more time here. Genes are coded for in your DNA. We've all heard about this. Genes are ultimately instructions for proteins. The DNA, the word is transcribed, which means copied into RNA, which is then translated into proteins. These proteins then do something called catalyzation. They help perform certain reactions that are important to cellular function, i.e. they speed up chemical reactions. They make things that you've heard about like antibodies, albumin, hemoglobin, all the things that make us us are coded for by DNA to turn into these proteins that do things for us. Each protein is coded for in the DNA as 3-letter sequences in the DNA. And each of these 3-letter sequences relates to a code that's specific for an amino acid, which is the building block of proteins. So proteins are made of, say, 300 amino acids. and you have a 900 sequence code of DNA to code for those 300 amino acids that turn into protein. Changes in that DNA code will result in a different amino acid being used in that protein, which causes a different protein to be built. So I'm going to give you an analogy here. You're building a swing set for your kids or your grandkids. The swing set you're building is the protein. That's what you're building. The instruction manual is the DNA. The parts of the set, like the concrete, the wood beams, the braces, the bolts, the chains, all of that, those are all the amino acids. So you're looking at the instructions and you say, okay, I know I've got all these parts. You are the RNA. You're translating the instructions into putting the parts together to form the final form. If the instructions are correct, you get a swing set. If you are me, or the instructions are incorrect, you get a broken swing set. So let's say someone comes along and changes the instructions and calls for chains where one of the wood beams is supposed to go. We end up with a broken swing set. You followed the instructions exactly right. The DNA, the RNA, they did everything they were supposed to do. They followed the instructions. They ended up with a different swing set. Okay? What if the code seats get changed to bolts? No kid can sit on it. So this is the concept. Biology is very similar. Gene mutations change the instructions for what protein is formed. A different amino acid, or say bolts instead of seats, or multiple amino acids are changed, which gives you a different protein. You get a different swing set because the instructions changed. The different protein, if it survives, and we'll talk about that, performs a different function. For example, you have proteins that code for blue eyes. Something gets changed, now those same proteins code for green eyes. There are various methods for gene mutations to occur. I'm not going to go into that kind of detail. But once they do, once the gene itself in DNA is changed, when the DNA copies itself to pass on to your children, you now have that new gene. So we've got new instructions, new protein. If it's advantageous, we pass that gene on to our kids. At least so the evolutionists tell us. As you can imagine, and as will be something fundamental that I will try to emphasize many times, mutations are frequently, some would argue almost always, harmful. Almost every time you change what made you you, it turns out not to be a good thing. Now sometimes these are simply neutral. The protein can absorb one amino acid for another, and it really doesn't change that much. The theory of evolution is that these are occasionally, and I put that with a question mark because there are some questions about that, but occasionally a gene mutation may be helpful. Microevolution, as we talked about, occurs when an organism develops a new protein that gives it a survival advantage over its counterparts. We talked a little bit about this last time, but a bacteria develops a protein which acts as an antitoxin to penicillin. We all know penicillin is an antibiotic, should destroy a protein. This bacteria, should destroy a bacteria. This bacteria develops an antitoxin that actually destroys penicillin. Now this bacteria can survive. And now this penicillin-resistant bacteria survives when the penicillin-sensitive did not. This is microevolution. And as long as the selective pressure of penicillin being around remains, this particular bacteria that has this mutation will have a selective advantage over the other bacteria. The theory of macroevolution is you get multiple gene mutations like this that result in a new species. So I hope that makes that a little more clear. Again, happy to take questions on it at any time. So, goals for the course. We've gone over the fundamentals of evolution. For the next 2 weeks, we're going to focus on why is the theory so flawed. I think if you didn't get a copy of the syllabus, there were some extras in the back along with some of the books that I recommend. If you have any questions about those, let me know. If I need more, I can make more copies. As you can see, we will get into other things about age of the Earth, Big Bang, radioisotope dating, etc., etc. But tonight and next week, the focus is purely on evolution and why the theory is flawed. So, this is Darwin's problem with scientific evolution. And remember that Darwin came up with this theory around 1859, okay? When he developed this theory, cellular biology, what I got my degree in, wasn't really a thing. didn't really exist. All they knew was that cells, if you took a cell, that's the individual building block of an organism, that it was made of two structures, what they called protoplasm, which was all the goo in the cell, and the nucleus. That this is literally what they would see under a microscope, and this is all there was. They didn't know about DNA, they didn't know what was in here, it was just protoplasm and a cell. And so Darwin said, great, I can work with those two components, we'll just evolve things from there. And genetics really wasn't understood for a long period of time. In fact, many of us weren't even born when the double helix was written about in 1953. Some were, and that's okay. So a cell this simple makes evolutionary theory a lot easier, right? Everybody can picture this. There's two components to the cell. We're just going to change the cell a little bit. It's all protoplasm. Well, what we found is the cell is much, much, much more complex than Darwin ever understood. The reality of the cell and cellular biology is far more complex. And the more we learn about science, the harder evolutionary theory is to swallow. And my ultimate goal in showing you some of this goodness is that I want you to understand that evolution is a faith-based theory. Ultimately, scientists approach it as a non-falsifiable theory. And if you're not familiar with that term, it basically means in science there should always be something that can prove you wrong. Try asking an evolutionist what can prove them wrong sometime. They will always have an explanation. And if you have a non-falsifiable theory, if there's nothing that can prove your theory wrong, that's called religion. So looking briefly at the cell, this part in purple here, this was the nucleus from the previous cell. Okay, last week we talked about the complexity of the DNA, the 6 feet of DNA you have in every one of your cell, and the complex winding and interaction that occurs here. What they called the protoplasm is full of all kinds of things that I'm happy to talk to anybody about afterwards if they're really interested in this. But suffice it to say, the cell is an incredibly, incredibly complex machine. It is not simply protoplasm and nucleus. So I'm going to focus on 3 different problems tonight and then several problems next week. And so I've broken these down into different sections here. The first problem is something called irreducible complexity. This book by Michael Behe came out, I want to say, in the late 90s. Fantastic book. This is one of the best books I've seen on evolution. This guy is a scientist, and ultimately he wrote this as a challenge to evolution. This sums up very well my fundamental problem with evolution. But the ultimate concept here is some structures are just too complex to have evolved one gene at a time. Remember, we're changing one thing in the instructions. We're changing bolts for seats. We're changing wood for concrete. Okay? Take away one part of the system, and the entire system is useless. So certain systems, in fact most systems in a human body, or even simpler organisms, this is a picture of a single-celled organism, require multiple parts to function. And these include things like the clotting cascade that I'm going to come back to, the immune system, or even this little tail called the flagellum, which simple single-celled organisms use to get around. It creates propulsion for them. This is an incredibly complex organism. And I'm not going to go into the details of the flagellum, but Behe has a whole chapter on it that is very, very interesting. Now, so I'm going to try to simplify this a little bit. I want you to think of this in terms of everyday items you use. A blender, a car, your TV. What happens if you take the blades out of your blender? Doesn't do much, right? What if you take the tires off your car? Okay, do you still have a blender or a car at that point? No. Those systems are irreducibly complex. You cannot have a blender with all parts there. So now, go ahead and design that blender or a car with these are the restrictions. Each part has to independently function. It has to do something on its own. Those blades have to do something useful by themselves without any propulsion equipment. Each part of the car has to do something. With each addition of each part, that device still has to function, but also be an improvement over whatever you started with, so that there's no longer a need for the prior model. So let me put it in terms of the car. Let's start with a seat. We're all sitting in seats, right? It's a comfortable place to sit. Let's put some wheels on there because we know wheels are useful. We know seats have a purpose and wheels have a purpose. Let's combine them together. Now we've got a wheelchair. All right? We know a motor has a purpose. We'll take a wheelchair, we'll put a motor on it. Now we've got a motorized wheelchair. We know canvas has a use. It's used for clothing, houses. Let's cover the motorized wheelchair in canvas. Now you have a motor carriage. Now you got lights. We use lights for a lot of things. Let's add some headlights. Now you got nighttime driving. Seems simple, right? And this is basically the level at which evolutionists function. All these things, each independent step, seems to make sense in and of itself. But what about those details? Well, what's the utility of a steering wheel outside of a car? How about the brakes? Are those a lot of use all by themselves? Is a car useful with those things, without those things? So let's be really fair and let's really talk about what it would mean if we're using the car analogy at a fundamental level like they do in evolution. Where'd the motor come from? We started with a motor. Motor's a very complex thing. Make me a motor one step at a time by the same process I just showed you on a car. Make me the original wheel even one step at a time using those same rules. While you're at it, don't just assume you have processed metal and rubber laying around. You need to evolve ways to get those and process those things too. So back up and tell me how that gets done. Gets a little tougher, right? Well, Darwin in the 1850s, his understanding was at the very simple level that I was showing you. You start with a seat, you add some wheels, you make a wheelchair, okay? That was the protoplasm level Darwin understood these things. Adding in questions like the steering wheel and brakes were just some of the initial objections you might have. Irreducible complexity gets at the last level of what I was talking about. Where do you get the raw materials? How do you get the raw materials out? How do you do this one change at a time? Start with a clump of metal, leather, and glass. Now combine them in a way, one step at a time, where each step is functional and an improvement on the previous step until you get a car. The inability to create that car in this way is called irreducible complexity. The complex product doesn't work unless all are present and functioning. Make sense? Okay. So, living organisms, far more complex than machines, okay? We all are impressed by Henry Ford and Steve Jobs and wish we had their creativity and their money. But what they did pales in comparison to what God does. With all of our intelligence, we don't begin to understand most things about God's creation. That cell I showed you, that's an incredible oversimplification of what I knew about the cell back when I was in college in the late 90s. I am sure it's way over my head now. But let's take an example from human biology. I want to talk specifically about the coagulation cascade, which is blood clotting. So blood clotting is a very complex, very well-balanced system. If you clot too easily, you'll die from things like pulmonary embolism that you might have heard of. If you don't clot well enough, you will die from things like brain bleeds, brain aneurysms. The signals to tell your body to clot have to be incredibly well regulated. The way clotting works is platelets, which we've all probably heard of, components of your blood, they form a physical clot, and something called fibrin stabilizes the platelets. So the platelets are kind of like the chain links, and fibrin is the glue. This coagulation cascade, as a quick side note, this is what I do day in, day out. The picture I'm showing you here is the formation of a heart attack, just as an FYI kind of side note. This is the, can't help myself. A heart attack is loss of blood supply to the heart. The heart, like every organ in the body, needs a blood supply. When it pumps blood, the first branches supply the heart itself with blood. Over time, those arteries can build up with plaque, and blood, which is represented by these red blood cells, tries to get to the heart. Eventually, for reasons we don't understand, this plaque ruptures. All this stuff underneath spills into the bloodstream. All the bloodstream knows how to do when it panics is form clots. Clots are heart attacks. When you block off blood supply to the heart, you get no blood to that part of the heart starts to die. This is all an incredibly well-regulated system, this coagulation cascade, this clotting. and has to be thoroughly, thoroughly regulated. Otherwise, we'd all be having heart attacks all the time. So how does it work? Well, if you cut your finger, we all know that eventually it clots. So a cut tells the platelets, the clotting part of the blood, go ahead and start adhering to each other. This same cut activates a series of proteins that we talked about that catalyze reactions, that cause certain things to happen. This will cause this initial platelet plug to harden. And then the end of that series of the clotting cascade is when something called thrombin activates fibrinogen to become fibrin, and this is the concrete that seals up the plug. This is, again, sort of very broad explanation, but you have a cut, the platelets initially close it, eventually they get signals for fibrin to seal it. So this is just the graph itself. You have a damaged blood vessel. The platelets become activated, and they form this initial clot to try to stabilize things. You can see this every time you cut your finger. You'll notice you ever cut your finger and then accidentally knock it loose again? It's because it hasn't had time to do this rest of this stuff. But you initially clot it off with just platelets. Then you get the coagulation cascade, which eventually activates this substance called fibrin, which is the glue, if you will, that holds the platelets together. And that's your clotting cascade. Now, I'm not going to go through this in detail, and there'll be no test on this. But the ultimate goal of the cascade is to generate that fibrin. That stabilizes the platelets. And thrombin is the step right above it. So thrombin has to be activated to form fibrin. There are, and again, this is even an oversimplification, but I just want you to appreciate the steps on how this happens. There are two ways to activate blood clotting. There's what is called the intrinsic pathway, which is kind of how we prevent internal hemorrhage every day. And then there's the extrinsic pathway, which is your blood is exposed to something else, say the air, which tells it to happen. So in the intrinsic pathway, you start with factor 12. And 12 activates 11, which activates 9, which activates 8, which activates 10. Yes, they discovered them in different orders. Which then 5 separately comes in and combines with 10 to activate 2, which is called thrombin, to activate 1, which is fibrin. But fibrin needs a stabilizing factor they discovered later called 13. Got it? Okay. And then there's the extrinsic pathway that works a little different. This also has what are called feedback loops. You see in green here, these things that say thrombin, thrombin, thrombin. Well, as this thrombin, 2 is formed, it comes over here and says, hey, let's form 13. Let's turn 5. Let's activate 8. It's a self-perpetuating thing, okay? Does anybody know who this is? Yeah. What is it? Romanovs. That's right. That's right. The last Tsar of Russia, right before Putin. Just kidding. So this is Tsar Nicholas II. Some of you, if you have kids like I do, might have seen the movie Anastasia or the cartoon Anastasia. I believe that's Anastasia. Does anybody know who this is and why I'm highlighting him? Very good. He's a hemophiliac. This is Alexei. Some would argue that he is ultimately somewhat responsible, not him personally, but his illness is responsible for the fall of Russia because his mother, became very, very, this background story, I was actually looking this up again last night. So obviously in royalty, they always want to have a male heir. And she gave her husband 4 female heirs. And she was finally able to give him a male heir, the 5th child. And unfortunately, he was born very, very ill. And she was overwhelmed by how ill he was and consulted with somebody named Rasputin that we probably have all heard of. And some would argue that that relationship and the relationship with Rasputin is what drove a lot of the chaos that ultimately led to Lenin, that led to the awesomeness that is communism that now exists in Russia, or did exist in Russia. So, background on that. But hemophilia, it's a disorder of the coagulation cascade, specifically a lack of either factor 8, factor 9 or factor 11. Now, I was always taught it was factor 8, hemophilia A, that Alexei had. I actually looked it up last night. He actually had hemophilia B for your trivia buffs. Doesn't matter. The point is a loss of any of these factors, despite the presence of all of the rest of them, and they all work fine, leads to massive bleeding and usually early death. Couple other ones just for trivia. Factor 5 Leiden is a mutation of factor 5 that makes it insensitive to protein C, which is a separate factor I didn't even put on there that makes clot formation more likely. These people are prone to clotting. Something called prothrombin gene mutation is caused by a single DNA molecule. One letter of the 3-letter code got converted from a G to an A, which results in a totally different protein called the prothrombin gene mutation, and that's that factor 2, makes it much more prevalent, and these people are very, very high risk for clots. So this is a lot of what we do in medicine all the time. We have people come in with clots, and it turns out they have these genetic disorders. This whole cascade has to be extremely balanced. As I said before, this chart doesn't do it justice. A slight variability leads to severe disease, and more commonly death. Now, I didn't even go through, and nor am I going to go through, the undoing of a clot. If we just clotted everywhere all the time, we'd die from that. But there's a whole separate entity to undoing clot, and that has to be very well balanced with the clotting cascade itself. So here's the challenge. Give me that one step at a time based on what I've shown you. Remember, each factor needs the one before it, and each factor is useless with one single missing piece. What's the point of having all the factors except factor 8, known as hemophilia, or factor 1, which actually we don't even see because it would result in death? The whole system is useless unless each individual component is there. It simply cannot be evolved one step at a time. What I've shown you again is an oversimplification. There are numerous other things that I could show you, other components, other aspects, many of which we use in modern medicine. A lot of what I do every day targets specific factors there. And I talked about feedback loops, which are basically signals tell the signals behind it, hey, I'm working here, you work harder back here. Okay? So a small signal can tell the ones way back here, I need a lot more of what you're doing. And we didn't even discuss the resolution. And again, if they never dissolve, we would die. This is an intricate and perfectly designed system that is constantly working to keep your blood delivery perfectly balanced. Couple other examples of irreducible complexity. The immune system. Immune system is a great example. The immune system is fascinating. It's one of my favorite topics. There are multiple cells involved in the immune system. I'm sure everybody here has heard of the human immunodeficiency virus, HIV, that causes AIDS. It knocks out a single type of cell, something called the T4 cells. Every other system in the immune system, the B cells, the plasma cells, the megakaryocytes, the T8 cells, I could go on and on, they all work fine. One type of cell in the immune system doesn't work, and until recently this was lethal, and everybody died when they got HIV. Bayes' book does a really nice job of explaining that flagellum, that tail that I showed you, and the point of that, and I'm not going to go into details of that, but his point in discussing that is that evolution is impossible even in single-celled organisms. I give you an example of humans. He takes it back to some of the simplest cells that we have and goes over why even those simple cells, we still have irreducible complexity problems. So let's look again at the giraffe's neck that we talked about last week. It's not just a cute cartoon of a neck getting bigger. Has anybody ever stopped to consider what kind of heart it takes to pump blood that high? In fact, I had this discussion with one of my partners who wanted to argue with me this week. He didn't have a good answer. And what happens when that giraffe bends down his big neck? Have any of you stood on your head lately? We all see kids do it, right? But have any of you done it? Do you know how that rush of blood you get to your brain? You can't do it for very long. Imagine a giraffe. If he bends down, it's amazing he doesn't bleed to death instantly right into his brain. You simply cannot do that one gene at a time. So in summary, there are multiple systems in an organism which require multiple parts. Sorry, not to Marco Rubio it here for those who remember that. And each of those parts is made by multiple genes. Each part is completely dependent on the existence of the other parts in order to function. Therefore, it's impossible to form the entire system one gene at a time. Before I move on to statistics, any questions about that? Yes, ma'am. Mm-hmm. Correct. You cannot get these complex systems with one simple gene mutation. You turned on your playground, you turned your seats into bolts. And that's all you did. Yet the whole playground can't exist. You need everything there or you've got nothing. Very good. All right. So turning to oh yes, sorry.
What do the evolutionists purport as their reason for how these complex systems all form at the exact same moment they all need to form the complex system at once?
Because science, you religious bigot. They don't have a good answer. They really don't. And honestly, if you try to look it up, you will mostly get almost exactly what I told you, because science. Because how dare you question? They don't spend a lot of time answering these questions because they think they're silly to even pose the questions. Again, you're questioning their religion. And they have a non-falsifiable belief, so they will come up with something. And we'll talk a little bit more about that when we talk about the Big Bang and how non-falsifiable they make that belief and how they just sort of create in their own minds explanations. So no, I have not seen a good explanation of what their answer is. All right. So I'm going to move on to statistics. This was something I actually had fun putting together. So what are the true odds of something happening by random chance? Depends on what we're talking about, right? Chance of heads or tails a single time, 50-50. All right, now I want you to flip heads 8 times in a row, 1 in 256. And you could probably flip a coin enough to do that. How long would it take you to get 20 in a row when your odds are 1 in 32,768? Long time, right? So evolution often gets compared to monkeys with a typewriter. Give enough monkeys, enough time, and eventually somebody's going to write a Shakespearean sonnet. Okay? But will they really? So let me take you through this. How long would it take a group of monkeys to write this sentence? And I mean this literal sentence. Okay? I'm not Shakespeare. We're just going to write with a simple sentence. Okay? We're going to give a monkey a typewriter with 26 letters, a space bar, and a question mark. We're going to skip the complexities of the shift key. Okay? So there's 28 different options for them. They have a 1 in 28 chance of getting each character correct. The above sentence is 65 characters long. There's the odds of typing the above sentence by random chance. I cannot pronounce that. Well, let's get a lot of monkeys with a lot of typewriters and lots of time on their hands. We're now going to give 10,000 monkeys 20 years of typing, no breaks. We're going to do this the Chinese way. Sorry. I buy my Apple products, but sorry, rude. My wife's going to kill me. Sorry, don't quote me on that. All right. Let's assume each monkey can type 5 sentences every minute. That's 65 words a minute. That's faster than I can type, and I consider myself a good typist. Okay, those monkeys will create 525,600,000,000 sentences in those 20 years of no bathroom or coffee breaks. Those are your odds now. So let's simplify that. There's your odds. If somebody can pronounce that, let me know. Okay, Ross, you just don't, and I got told this the other day, you just don't understand how long a billion years actually is. You're just not contemplating the amount of time here. All right, fair enough. We're going to give those monkeys 1 billion years. But let's increase it to 100 trillion monkeys, just to make it more realistic. Here's the new odds. And let's simplify that again. I still can't pronounce that number. Here's comparative odds. We've all played the Powerball or the Mega Millions lately, right? And we all think we're going to win. I don't know if anybody knows anybody who's won, but there's a number I can actually pronounce. What are the odds of being struck by lightning twice? 1 in 9 million. There's probably no clear answer on when I actually tried to look this up. When is something statistically impossible? And I will get to one of the explanations somebody tried, but I think that's about as close to statistically impossible as you can get. And that's a monkey trying to create one sentence. Okay, let's do this with a protein. Remember, there's 20 amino acids that make up proteins. That's your protein alphabet. Let's make thrombin, that thing I kept talking about, the clotting factor. 295 amino acids long, no problem. So it's 1 out of 20 to the 295th power. I couldn't get even my Apple calculator to give me an answer for that. The number was simply too large. And that's one protein in one part of the coagulation cascade. So I hope you're realizing the evolutionist answer of it just took a lot of time is meaningless. Some things become statistically impossible and unfathomable. So as I was looking for my answer on what is something statistically impossible, somebody knew what I was getting at. So somebody tried to write a proposed answer to this, and it involved a number of, I'm not going to go into all the details, but I read it for a long time. I called my dad, who has an interest in this topic, and we talked about it for a while, but a lot of what he thought had a bunch of suppositions and theories about how we can't use modern life to tell us what was at the beginning, and it was much, much, much simpler, and they came up with this idea sort of to answer your question on they'll always have a theory for something. Well, it must have been self-replicating RNA surrounded by lipids, something that doesn't exist in nature, but it must have back then. And there is, of course, no evidence of this. Why did it die off? We still have bacteria, supposedly the beginning of evolution. And this becomes very similar to what we're going to see in the fossil record as we start to talk about that. You got to start with the idea evolution is a fact and work backwards, no matter how silly the explanation is. So they will all, I do give them credit. They had a very lengthy explanation on chemical events, on a primitive Earth and the numbers, and again, involved a whole bunch of assumptions and ideas about available material, where these amino acids came from, etc., etc. I am going to come back to next week the question of where did the amino acids come from when you're an evolutionist, and most importantly, they had the idea that this all occurred in water. Water would absolutely destroy amino acids. We will talk about that next week. So even if I grant some of that, even if I grant this guy his theory that he was able to finally get self-replicating RNA and something, they had a long way to go to that full Shakespearean sonnet. He might have gotten the first few letters of my sentence, but did you get to the fully functioning cell or a fully functioning organism? And that entails odds that are countlessly bigger than the numbers I showed you here. So let me give you my father's example. He loves this one. So he likes to ask everybody, are you or any human smarter than random chance? Well, of course I am. All right, fine. Let's put all the parts for a jet engine in 2 rooms. One has an aerospace engineer with computer modeling available. The other has you, blindfolded. Who's going to build the jet engine? It's actually worse than that, though. Why do you get all the parts? Instead, we'll put you in a hardware store, still blindfolded. This time we're not telling you what we're making, because after all, it's just random chance that creates sophisticated structure. Now go, build the engine. That's too simple. Where'd the hardware come from? We're going to put you on Earth. There's iron ore, copper, etc. You're still blindfolded. Create all the necessary tools and parts from scratch, blindfolded, and you don't know what you're making. You just know you need to, quote-unquote, advance. You need to naturally select. Does anybody think a jet engine could ever occur by random chance, or does it require intelligent design? Any questions on statistics? Okay. Yes?
For people who may not know, what is the 295 behind
How many for thrombin?
Yeah.
That is how many amino acids are in thrombin.
The 295 means how many?
So thrombin is a protein made of 295 amino acids. So you have a 1 in 20 chance. There's 20 amino acids. You have a 1 in 20 chance over 295 slots to get the right one. So you might end up with amino acid A in slot 1, or B or C Do you see what I'm getting at? Does that make sense? Okay.
I heard someone before that was like a simple way to explain that was how many zeros would be behind that number.
Oh, yeah. It's when you do 20 to that power, it throws it off a little. I couldn't get it. The point is, it's a huge number. But yes, but thrombin is made of 295 amino acids. That's actually a fairly small protein. A lot of proteins are bigger than that. So I just used that one because we had talked about the coagulation cascade. All right. So intermediate species, and I think this is the last topic I have on this tonight. All right. So we talked last week about from goo to you by way of the zoo. So you start with the Big Bang. You work your way to what are called eukaryotes. Those are sophisticated single-celled organisms, to bacteria, to fungus, to fish, to reptiles, to mammals, to primates, to us. And it makes sense. It's a beautiful cartoon. I love the cartoons they come up with. And then you've also got the fossil layer, right? That we see, oh look, conveniently the most simple organisms are at the bottom. As we work our way up, they get more sophisticated until they finally become what we see today. So evolution works on the principle of slowly improving an organism over time. That's what we talked about. We're slowly adding features. We're slowly adding to that giraffe's neck length that allow this organism to somehow have an advantage that pass its genes on better than its predecessor. So a fish that, say, can partially breathe outside water, it can better escape predators. So it has an advantage over the fish who have to stay in the water and get eaten. A lizard with wings can more easily capture food. A human with 2 hands can beat the snot out of the guy with only 1 hand and win the girl. Okay? Each step results in a superior being. These steps are driven by environmental pressures like the scarcity of food, changing temperature, presence of predators, things that selectively help you have an advantage over another group. So where are these intermediate forms? Where is that human that just had 1 arm? Or the chicken that sort of looks like a dog? Or the bird that has gills? In theory, each of these intermediate species should have been functional enough to outlast its predecessors. But where is it now? Darwin himself actually acknowledged this was the biggest flaw in his theory. But what he said was, no problem. The fossil record will tell us eventually. We just haven't found it yet. So the often given excuse is that these animals died off because of ongoing pressure to change. Fair enough. But this begs the question about why the predecessor is still here. And we'll talk a little more about later. The other excuse is they're in the fossil record. All right. So the theory is that, again, the depth of the fossils correlates well with the age of the animals at that time. So sedimentary rock, which we'll talk about in great detail later, these are layers that we're told are slowly laid down over millions and billions of years, and they slowly build their way up, and thus the newer animals and the newer layers are at the top. And I'm sure we've all seen drawings like this with well-labeled time frames working our way up to modern man. Anybody heard of the Cambrian explosion? I wouldn't necessarily expect you to, but this is something that comes up a lot. The Cambrian explosion, well, what is that? So backing up just a second, the Cambrian period is right here in the fossil record. I want you to pay close attention to the very bottom. There's not much here, and then there's something here. So what was the Cambrian explosion? Well, it's the part of the fossil record referring to what they call the Cambrian era, which was 450 million years ago, where suddenly we find most of the animals in the fossil record. Those earlier layers, contain very simple organisms like sponges and jellyfish, and then suddenly we get fully developed animals, even ones we know today, like insects and crabs and even some vertebrates. We can't find any intermediate species. We basically went from nothing to everything. There are no intermediate species when we get to the Cambrian explosion. Now, some evolutionists will posit that the transitional forms were soft-bodied. And you see, Ross, soft-bodied organisms don't create fossils. The problem is they do, in fact, create fossils. That's why we have fossils of jellyfish and worms, and even fossils of single-celled organisms. Okay, but we get this other explanation, that we simply have yet to find the critical missing link. Well, here's the problem. We actually have found millions of fossils at this point. and plenty of rocks with sediment from that pre-Cambrian era, and we still got bupkis. It's highly unlikely that we're missing something. So, missing links. We all talk about the missing links. And most of the missing links that people refer to, it's usually referring to getting from ape to man. And we're going to talk about those next week. But I want to talk about a couple that are in the not ape to man. And it's always important to carefully examine these and see if they meet the criteria of a missing link. So Archaeopteryx, which I practice saying a lot, is this animal right here. And this was discovered conveniently shortly after The Origin of Species was published, thus proving a missing link between reptiles and birds. And it was hoped to be one of many fossils that discovered that would be a missing link. However, this is simply one of the many strange animals out there. Has anybody ever seen a duck-billed platypus or heard of one? I've heard of them. I've never seen them. Even if the Archaeopteryx is transitional, which it's not, where are the steps on either side? All right, you found one fossil. Where are the steps on either side? However, it turns out, carefully looking at that animal is clearly an extinct bird. It's not a reptile. And even if you accept it as a link, where are all the others? Well, all right, we got Archaeoraptor. Fascinating fossil. Don't know if anybody remembers this being reported in National Geographic in 1999. Huge news. This fossil was purchased at a mineral show in Arizona, and it showed a tail of a dinosaur with the forelimbs of a bird. Incredible, impressive, important missing link. And it shows the presence of feathered dinosaurs. This copy of National Geographic was hard for me to find, because it was a problem. It was a complete fake. Somebody literally glued a dinosaur tail to a primitive bird. This, and some scandals that we'll talk about in the future, simply serve to show the fury with which evolutionists will proceed to prove their failing theories. So, the fossil record should be overflowing with intermediate species and missing links. So should the living world, by the way. I mean, there should be that dog-chicken mix out there somewhere that we keep as house pets to lay eggs. But we haven't found them yet. So much of what you see in biology textbooks is simply creative art based on single bones, and often corrupted ones. They take a single bone and draw an entire beautiful picture around it. And then sometimes, if they're even remotely honest, in the corner you'll see the two little bones that they actually found from which they drew the whole structure. And the biggest issues is that these scientists start with the conclusion that missing links exist, and then they search desperately to find them, rather than asking whether or not evolution is the best explanation for a planet of diverse species. This is that non-falsifiability that I'm going to hit on multiple times during this talk. So in conclusion, we've hit on several issues with evolution. The irreducible complexity issue, the statistics issue, and the missing intermediate species. Next week, I'm going to continue to look at these various holes and flaws in evolutionary theory. I have several more subpoints that I want to talk about. But I'm going to stop here, and I'm happy to entertain any questions anybody has. So, thanks. Oh. Yes, sir.
One of the things that I've heard is an argument for macroevolution, that those intermediate species never stop existing, they live all the time.
Mm-hmm.
And that all the animals on the earth are products of those things. They exist with us, and then not everything evolved the same way at this stage of time.
Mm-hmm.
All those stages of evolution currently exist together.
I mean, I've heard that to some. You're right. I mean, the part of it is the theory is that yes, you separate it into multiple pathways of evolution, so it's not directly cells to man. It's cells to this line, something to this line. Yes, but I still don't think that answers the fundamental in between species. I mean, ultimately, the reason we have our classification of animals, that kingdom, phylum, class, order, family, genus, species we all had to memorize, was because we can distinctly identify kingdom, phylum, class, order, and we don't have somebody. I mean, is there a species where somebody says, gosh, I don't know, it's sort of this genus, it's sort of this genus, and we don't have that. We have everybody speciated quite well. So I still think you're missing, not you, but they are missing the every intermediate species that you would have. Again, it's sort of like even look at human evolution. I mean, yeah, we come in all shapes and sizes, but we all fundamentally have the same immune system, the same muscular structure, the same 2 arms and 2 legs. I mean, my dad's always joking when he's working on something, I need that third arm from evolution. This would be so much easier if we could just get that third arm in there, and make that happen. So, good. Yes, Dave. Yeah. Mm-hmm. 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 Correct. Yes, and I agree. And even evolutionists are ultimately seeking some sort of explanation, right? I mean, if they're going to deny God, they still need some. We're all hunger for some sort of explanation, and so, which is why I always come back to evolution is religion. It's just it makes them feel better to call it science. So, yeah, it is. I know. Yeah. Yes, sir. The epigenome. You have to tell. Mm-hmm. Mm-hmm. I haven't heard the term epigenome, so I apologize. But you're right. I mean, when the body gets exposed to certain stresses, yes, you start upregulating certain genes that you wouldn't normally, and in stressful environments, you may start to produce more of something that you didn't before. And yes, those codes were always there. I've not included it in this talk, but one of my dad, I keep going back to my dad because I told you he loves this stuff too, but one of his big things is something called genetic entropy, which is basically the theory that our genes are actually devolving over time, that God created us with an incredible genome coding for all of what man should ever be, and basically was created perfect, right? We know that. And over time, so Adam, if you will, had the genes to basically code for every race, every color, every body type out there, and now we're seeing the devolution, and we're seeing what is called genetic entropy meaning worsening of, and so you're getting less and less and less and less and less, and actually we're getting worse and worse. It's like that old movie Idiocracy. I don't know if you ever saw that, but so the same idea, yes, our genes certainly code for more than what we're using every day, but there are fundamental genes that must be there to make you human. So I'll have to look up epigenome. I haven't heard that, so I apologize. I can't give you a more intelligent answer than that. Yeah. Mm-hmm. 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 Would have, yeah, because it doesn't work, right? His theory was we're getting better with time. I mean, ultimately, you're right. I know what you're saying about descent of man, but yeah, in theory, in evolution, we're supposed to be getting better. So, yes, ma'am. Mhm. Mhm. Yeah. Mhm. Mhm. Well. Mhm. Sure. Yeah. No, I think that's yeah. It is. It well, hopefully it's not. Yeah, I mean it is. We ultimately know, right? It's all dire, and we all ultimately end with the end of the world and God takes over. But that not a reason to. Yeah. So, yeah. Did you have a question, sir? You mean am I planning to talk about it or? I I don't have anything specific on plants or trees as it goes with evolution. There are some things about the age of the earth that we'll talk about briefly with plants and trees, but no, I focus mostly on the animals, and that's an interesting question. I haven't actually given that much thought. I probably should. I mean, what is the selective pressure for a bush to become a tree? I actually don't know, and that's a really good question. But yeah, I haven't given that a lot of thought, but that's fair question. Was there a specific about that? Oh, well, you probably know more than I do. I mean, it's. Mm-hmm. Yeah. No, I think that's a fair point. I mean, I think you could apply a lot of these same principles to the trees. You know, the complexity of how nutrients go from the root to the leaves, it becomes very, very complex. That also has irreducibly complex systems. But yes, I skirted botany in college, so I am going to plead a little bit of ignorance. So, yeah, good. Yes, sir. Uh-huh. Uh-huh. Mm-hmm. Yeah. So great question. Probably a 6-hour lecture. It's um, in short, when you are a single-celled embryo inside your mother, you have all the genetic code to form every organ in your body. And over time, as the embryo develops, different parts and those cells are dividing incredibly rapidly, but over time, the cells do what's called differentiation, where basically it turns on certain genes to say you're going to be a cardiac cell. It turns on certain genes to say you're going to be a liver cell and turns off the others. But in theory, any cell in your body still codes for all of you. And this actually, that point and that question is actually makes me awestruck at God every time, because we don't begin to understand how or why that works. We pretend we do. We talk about DNA and we say, oh, isn't this fascinating? Well, I mean, how can one cell code for all of this, right? So it's a great question. We know in broad strokes how we think that happens, but the reality is I don't think we fully understand that. I mean, the fact that every one of your cells, that's why you do the little cheek swab to do the 23andMe, and we know everything about you based on a cheek swab. We know what your liver should look like, right? But that's not a liver sample we're taking. So, yeah, I don't think we fully understand how all those things work. I'm not sure we ever will, and one day I look forward to asking God if He'll let me. uh-huh. Correct. That's genetic entropy. That's that term entropy. Correct. I didn't include that in the talk, but there is something called the second law of thermodynamics that you may hear discussed, which is basically we all tend towards chaos and things tend towards disorder. You're right. That is one of the fundamental problems with evolution. It is the idea that somehow things get better when that contradicts everything else we know in science, right? It's like just how we all age, we all get worse, we all get nothing really gets better. So, yeah, wine. Fair point. Fair point. Yeah, yes. Well, I mean, yeah, yes. The technology is always getting better. I mean, the best example there is ultrasound with human embryos, right? I mean, we're seeing incredible things that people didn't. Suddenly, you can see a face inside the belly at a very young age. So yeah, things get better. I mean, sure. Every time I'm reading a heart ultrasound, I'll bring my partner. I said, "What is that? I don't know. You guys have any idea what that is? I don't know. Ignore it. Okay." So, but that probably makes you feel good as a patient, right? But it's so yeah, I mean, there's always little things we see, but yeah. 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 Or I was gonna say, or panic. Yeah. So. Yeah. Mhm. Yeah. Yeah. Correct. Yeah. Good. All right, guys. Well, hey, I appreciate the turnout. We'll be back next week and talking about evolution for the second week before we move on, and I'll be around for a little while afterwards if you have questions. And feel free to email me if that works better too. Thanks, guys.